how high is that star? I mean, really, what time is it precisely? And where am I geographically just by looking up at the sun? It still kind of blows my mind that ancient astronomers with, well, really just their sharp minds and some pretty basic tools could actually figure these things out, and with amazing precision.
It really is incredible. They weren't just, casually stargazing.
Yeah.
They were actively measuring the sky. And crucially, they got that even their best measurements needed corrections.
Yeah, the sky was their laboratory, essentially. And these astronomers were, well, meticulous.
Absolutely. And their drive wasn't just theoretical curiosity, was it? It came from real practical needs. Things like accurate timekeeping, which was vital for, agriculture, religious rituals.
Navigation, too.
Yeah, fluid navigation across huge distances.
Yeah.
And setting up reliable calendars. All super important stuff.
Welcome back, everyone, to the deep dive. Now, last time we dove into Aryabhata's Golapada, that amazing text that sort of painted the picture of the celestial sphere for us. We talked about mapping the local sky, using concepts like the meridian, remember that imaginary north-south line running straight overhead?
Yep, through the zenith.
And the prime vertical, too. We even started looking at how Aryabhata calculated how long daylight lasts.
Right.
But today we're getting practical. We're looking at how all that theory, all that geometry, actually translated into real-world measurements and understanding.
Exactly. That's our mission for this deep dive.
Yeah.
To really get how Aryabhata's math and the tools they used let ancient astronomers figure out their position, both in time and in space.
Okay.
We'll be looking at how just watching shadows, simple shadows, could tell them fundamental things about where they were and which way was which.
And also why even straightforward observations sometimes needed tweaking, corrections.
Precisely, why corrections were necessary. It's all about unlocking key astronomical and geographical information using, honestly, pretty basic tools and some really clever geometry.
Okay, let's dive in. When we think about where something is in the sky, altitude is usually the first thing, right? How high it is above the horizon. And Aryabhata had a method for calculating this. It involves something called hour angle,
which we touched on back in episode 28. Basically time, but converted into degrees of rotation across the sky.
Right. That plus your latitude, where you are on Earth.
Exactly. Once you know your local meridian, and you know the time relative to when something crosses that meridian, that's your hour angle, and you know your latitude, your fixed spot, then trigonometry is your best friend.
Ah, trig. Knew it would show up.
Always does in astronomy. And Aryabhata, in his Dṛkgatijyā section, had already laid the groundwork. He defined these sine functions, his Chāyā.
Which weren't quite our modern sines, but related.
Sort of. They were ratios within a circle of a fixed radius. We often call them R sines. Think of it as doing trigonometry on a specific map or model of the sky with a standard size.
Okay, so bringing that together, Aryabhata gives us a fairly neat way to figure out altitude, at least for things on the celestial equator.
Yeah, he simplifies it nicely in verse Gola.28.
Yeah.
Essentially, he says, and this is the simplified version, you multiply the R sine of the hour angle by the R sine of the colatitude. Now, colatitude is just 90 degrees minus your latitude. Or you can think of it as the angular distance from your zenith, the point straight overhead down to the celestial equator.
Got it. 90 minus latitude.
Right. Multiply those two R sines together, then divide by the radius of their model celestial sphere. And what you get is the gnomon sign, or Śaṅku. That's Śaṅku.
Okay, and that value, that Śaṅku, that is the elevation.
Or represents it.
It represents the elevation above the horizon, yes. Yeah. Technically, it gives you R times the sine of the altitude, but it's the key value.
And this specific formula is for objects on the celestial equator.
Correct. It's a simplified case. For objects not on the equator, you need more complex spherical trigonometry, which they also developed. But this principle is powerful. How so?
It shows that connection, right? Time and location let you predict position. It's a demonstration of understanding the basic geometry of how the sky appears to move from our perspective, even if their physical model of the universe was different from ours.
It really hammers home that interconnectedness. Know the time and where you are, you can predict where stuff is in the sky.
And the flip side is just as important.
Right. If you can measure the altitude of something and you know where it should be at a certain time, you can work backwards to figure out the time, or even your location.
Exactly. The sky becomes this enormous, predictable clock and a navigation chart all rolled into one.
So how did they make these measurements? You mentioned tools.
Well, one of the most fundamental, most versatile tools was the gnomon. or Śaṅku, using Aryabhata's term again.
Which is?
Basically a vertical stick, a rod, a pillar, standing perfectly upright on a perfectly level surface. Sounds almost too simple.
Just a stick in the ground?
Pretty much. But the shadow it casts, the Chāyā.
Chāyā. That's C-H-A-H.
Chāyā, exactly. The information they could pull from observing that shadow, it was, well, remarkable. It's kind of amazing what you can learn from a shadow if you watch it carefully.
So Aryabhata's system really leaned into observing this Chāyā.
Absolutely. You track its length, you track the direction it points throughout the day, and suddenly you can unlock some pretty sophisticated geographical and time information.
How did that work? What could the shadow tell you?
Well, Gola.29, the verse, it's quite brief, but it describes calculating the shadow's components relative to the cardinal directions, north, south, and east-west.
Okay.
He talks about the north-south part. It's called Yamya. That's Y-A-A-Mya if it points south. And Samya, S-O-W-M-Y if it points north.
Yamya and Samya. Got it.
And then the east-west component is related to something called Pragoda. That's P-R-Guna. By carefully measuring these components, or just the shadow's tip, throughout the day.
You map the sun's path.
Effectively, yes. You map the sun's daily journey across the sky for your specific location.
And that path must reveal some key things. You mentioned the shortest shadow.
Right. That's the crucial moment. The shadow is shortest at local noon. That's when the sun is highest in the sky for the day, and it's crossing your meridian.
That north-south line, again, Aryabhata called it Dṛkchāyā.
Dakshi Natarye Shastam. Yes, quite a name.
Huh. Okay, so at noon, shortest shadow, and
critically, in the northern hemisphere at least, that shortest shadow points directly north. That moment tells you exactly where north is. It defines your local meridian.
Ah, so the gnomon shadow finds true north for you.
Precisely. Establishing that meridian line is absolutely fundamental. It sets up your whole local coordinate system for observing the sky. It's your baseline for timekeeping based on the sun. That simple shadow becomes a tangible marker for this invisible but essential celestial reference line.
Amazing. Just from watching a shadow shrink and grow.
It's the power of careful, systematic observation combined with understanding the geometry.
Okay, so we've got direction finding. What else? Aryabhata also talks about something called amplitude, Arkāgrā.
Yes, Arkāgrā. Arkāgrā. Amplitude is basically how far off from true east the sun rises, or how far off from true west it sets on any given day.
Because it doesn't always rise exactly east, does it?
Nope. It shifts north and south along the horizon throughout the year because of the seasons, because of the Earth's tilt. Arkāgrā is the measure of that deviation on the horizon.
And Aryabhata had a formula for this too.
He did. Verse 30 of the Golapada gives the calculation for the R sign of this amplitude. It depends on the sun's declination. That's its position north or south of the celestial equator.
Right.
And, again, your latitude.
Okay, but here's where it gets interesting. You mentioned something about the equinox.
Ah, yes. The equinox, which Aryabhata calls Vyavadain Vishuvadhyayane.
Vyavadain equinox day.
On the equinox, the sun's declination is 0. It's right on the celestial equator. So, theoretically, its amplitude should be 0. It should rise exactly east and set exactly west.
But Aryabhata noticed it wasn't always 0.
Exactly. He notes that the Arkāgrā might not be 0, even on the Vyavadain. Which seems weird, right?
Yeah, why would that happen? If it's on the equator, shouldn't it be perfectly east-west?
This is where later commentators, like the brilliant astronomer Bhaskara the Scare, offer some fascinating insight.
What did Bhaskara suggest?
Bhaskara, I suggested this non-zero amplitude, observed even on the equinox, might actually be an early hint, an awareness of atmospheric refraction.
Refraction, like light bending.
Exactly. When sunlight comes through our atmosphere, especially near the horizon where it passes through the thickest layer of air, the light gets bent, refracted.
Okay.
This bending makes the sun appear slightly higher in the sky than its actual geometric position.
Ah, so even if its true position is exactly east on the horizon.
The refraction makes it look like it's rising a tiny bit north of east, and setting a bit north of west, too.
Wow. So they might have been observing an atmospheric effect without having the full theory.
It seems plausible. Bhaskara's comment suggests they noticed a discrepancy between the simple geometric theory and what they actually saw. It's a fantastic example of blending theory with careful observation and trying to account for the difference. It shows they weren't just crunching numbers, they were looking closely at the sky.
That really elevates the work, doesn't it? They're noticing the imperfections, the real-world effects.
Mm-hmm.
Okay, speaking of real-world locations, you mentioned latitude is key. And back in episode 27, we learned Aryabhata gave the latitude for Ujjain as 22.5 degrees north. How on earth did they figure that out?
Well, this leads us to probably one of the most elegant practical uses of the gnomon, finding your latitude.
Using the stick again.
Using the stick and its shadow again. Yeah. Specifically, the shadow at noon on the day of the equinox. The Vivadavasa Vishuvadi Vivasa, as he calls it in verse 31.
The equinox again. That day seems important.
It's fundamentally important for this method. It simplifies everything beautifully.
Okay, walk us through it. Equinox day. Sun is on the celestial equator.
Check. At your local noon, the sun is crossing your meridian, its highest point for the day.
Right.
Now, because the sun is on the celestial equator, its altitude at that moment, how high it is above the horizon, has a very simple relationship to your latitude.
Which is?
The altitude is equal to 90 degrees minus your latitude.
Okay, so the angle down from the zenith, the point straight overhead to the sun,
is exactly equal to your latitude.
Okay, that's the key. The zenith distance at noon on the equinox is your latitude.
Precisely. And Aryabhata's verse 31 tells us that on that specific day, at that specific time, midday, the relationship between the gnomon itself and its shadow gives you the R sign of your latitude. He calls this value Akṣajyā.
Akṣajyā, JYH, the R sign of latitude.
That's the one. He also notes something interesting, that at the Earth's equator, things rise vertically, which makes sense if you picture the sky rotating directly overhead.
So the method itself, you need your gnomon, perfectly vertical, level ground.
Crucial.
Then, on the equinox, you wait for local noon. You measure the shadow when it's absolutely shortest. Yep. Now you have the height of the gnomon and the length of the shadow. They form a right-angled triangle on the ground, right?
Exactly. The gnomon is one leg, the shadow is the other leg.
And the sun's ray coming down forms the hypotenuse. Aryabhata called that Karna, yeah. So you have this triangle, gnomon, shadow, hypotenuse. How does that give you latitude?
Well, think about the angles. The angle between the gnomon, the vertical stick, and the hypotenuse of the sun's ray is the sun's altitude.
Okay.
The angle between the shadow on the ground and the hypotenuse is the angle down from the zenith distance.
Which is the latitude on this day at this time.
Bingo. So that angle in the triangle is your latitude.
So how did they get the angle? We'd use trigonometry, like tangent, right?
Shadow length divided by gnomon height is the tangent of the latitude.
We would, yes.
Yeah.
So Aryabhata's system relied heavily on signs, or R signs. So they'd measure the shadow, the gnomon height. They could calculate the hypotenuse, the Karna, using, well, the Pythagorean theorem, essentially. Okay.
Then the ratio of the shadow's length to this hypotenuse length gives you the sign of that latitude angle.
Shadow over hypotenuse is sine.
Multiply that by their standard radius, R, and you have it. Akṣajyā, the R sign of latitude.
Wow. That is incredibly elegant and practical. A stick, a shadow, one special day, and you know where you are north-south on the globe.
It's foundational. A really powerful technique using the simplest possible tools and keen observation.
It really shows their ingenuity, but we keep coming back to this idea of corrections. Even these elegant methods weren't quite perfect in practice.
Well, the methods themselves were geometrically sound, but observing from the surface of the Earth introduces distortions compared to a pure theoretical Earth-centered model.
Right, and this is where those Dṛkkarma come in.
Exactly. Dṛkkarma, Dṛkkarma. These are the visibility corrections. Adjustments needed because we aren't observing from a theoretical point at the Earth's center.
Okay, what's a major one?
Parallax is a big one. Aryabhata calls it Lambana, or sometimes Dṛggatijyā, Dṛggatijyā.
Parallax. Like holding your thumb out and switching eyes.
Exactly that principle. Your thumb seems to jump against the background. Astronomically, it's the apparent shift in an object's position because we're viewing it from the Earth's surface, not its geometric center.
So our viewpoint is slightly different from the theoretical center point.
Yes, and this makes a difference. It causes celestial objects to appear slightly lower in the sky than their true geocentric position would suggest.
Lower? Why lower?
Think about the geometry. Unless the object is directly overhead at the zenith.
Where parallax is 0, you said?
Right, because then your surface position and the Earth's center are on the same line to the object. But anywhere else, viewing from the surface means you're looking up at it from a slightly different angle than the center viewpoint, making it appear lower against the distant stars.
And this effect is bigger for closer objects.
Much bigger. That's why parallax is so important for the moon. It's relatively close, so the shift is noticeable. For distant stars, it's negligible with ancient instruments.
And Aryabhata calculated this, verses 32 and 33 deal with this.
Yes, they lay out the trigonometry to calculate the correction amount, which he calls the phala, phala, the result or correction needed.
Phala, phala.
And knowing this was absolutely critical for things like predicting eclipses.
Because the moon's apparent position needs to be spot on for eclipse calculations.
Totally. If you don't correct for the moon's parallax, your predictions for when an eclipse starts, how long it lasts, even if it happens from your location, will be significantly off. It really matters for precision work.
So parallax accounts for our position on the sphere. What about the sphere itself? You mentioned horizon dip earlier, the Chāyā.
Yes, the Dṛkchāyā. He revisits this in verse 34 as another correction.
Dṛkchāyā. Horizon dip.
Because the Earth is round, your visible horizon isn't a flat plane extending outwards. It actually curves downwards. It dips below the true geometric horizon.
Okay, I can picture that. The horizon drops away because of the curve.
And that affects observations near the horizon. Things like the exact moment of sunrise or sunset, or the measured altitude of something low in the sky.
And Aryabhata says this correction needs refining. He uses the word sashuddha.
Samshuddha, yes, refined or corrected.
Why refined? What might that imply? Was the basic geometric calculation not enough?
It's intriguing, isn't it? It could mean a couple of things. Maybe it needed adjustment for the size of the object. Like sunrise isn't when the sun's center clears the horizon, but when its top edge does. That requires a slight tweak.
Okay, that makes sense. Accounting for the disk.
Or it might again hint at accounting for atmospheric refraction near the horizon, which also affects rise set times and low altitudes. Maybe refined meant adding an empirical fudge factor based on observation to get predictions to match reality better, even without the full theory of refraction.
So sashuddha might mean make this match what we actually see better.
Possibly. It certainly shows they were aware that the simple geometric model sometimes needed adjustment to align with real-world observations. It underlines that commitment to accuracy.
These Dṛkkarma, then these corrections, they really highlight Aryabhata's dedication, don't they? It wasn't just about the elegant math. It was about making it work for actual observation, bridging that gap between the theoretical ideal and what you see standing on Earth.
Absolutely. That rigorous approach, acknowledging and correcting for observational realities, is what makes his work so powerful and enduring in the history of astronomy.
Okay, let's try and pull this all together. This deep dive has been fascinating. We've seen how Aryabhata used trigonometry and that incredibly versatile gnomon,
The Śaṅku,
yes, to figure out altitude, linking time and location. We saw how its shadow, the Chāyā, could pinpoint cardinal directions, and how incredibly that noon shadow on the equinox gave them latitude, the Akṣajyā.
Foundational stuff.
And then we got into the reality check, the Dṛkkarma. Corrections like parallax, Lambana, dealing with our place on Earth's surface, and horizon dip, Dṛkchāyā, dealing with Earth's curve, and maybe even atmospheric effects, all showing this drive for observational accuracy.
It provides a really solid, comprehensive system for understanding the sky as observed from Earth, and it sets the stage perfectly for tackling even more complex things.
Like eclipses.
Which
is exactly where we're headed next time. In our next deep dive, episode 30, we'll explore what might be one of Aryabhata's most revolutionary ideas: his explanation for solar and lunar eclipses.
Yeah, this was a huge leap, moving away from myth.
Completely. He proposed a purely geometric scientific model, all based on shadows. The Earth's shadow causing lunar eclipses, the Moon's shadow causing solar eclipses.
We'll get into how he actually calculated these events, the geometry of Earth's shadow, how big it is out of the Moon's distance. It was built directly on the principles we've discussed today.
It sounds like a major shift in thinking, from myth to math.
A pivotal moment, really. Applying this geometric understanding of the cosmos, derived from these careful observations and corrections, to explain these really dramatic celestial events.
It really makes you stop and think, doesn't it? When you consider our modern science, our GPS, weather models, all the incredible measurement and correction we do, how much of it builds on these ancient foundations.
The echoes are definitely there.
The ingenuity needed back then to get such accurate results with, a stick, some geometry, and brilliant observation, it's just astounding. Makes you wonder what fundamental insights we might be missing today by relying solely on our complex instruments. Could we still find latitude with just a stick on the right day?
A profound thought to ponder. The power of simple tools wielded by sharp minds.
Join us next time as we step into the shadows, literally to understand Aryabhata's groundbreaking theory of eclipses. right here on The Deep Dive.